All right, ladies and gentlemen, you should now have out that giant piece of 11 by 17 inch page. Take it out, take it out, take it out. All right, so now what we've got is we should have our column for alkenes and alkynes. So moving on to there. So we've got one column for alkenes and alkynes, and the first question is, where are they used? They are generally reactants for other compounds. The other possibility is sometimes they're used as fuels directly, such as the common material acetylene. Okay, so those are our two major uses, or where they are found. Going on. The next box is general structure, and if we divide up the column, we're going to find that our alkenes, as we've already talked about, are carbon-carbon double bonds, whereas alkynes are carbon-carbon triple bonds. So just carbon-carbon double versus carbon-carbon triple. So that's the general structure difference. Okay, so no surprise there. So moving on to the next box. Next question is, are there polar bonds? No. Just like the hydrocarbons, these have differences in electronegativity of 0 or 0.4. Both are nonpolar. Since the bonds are nonpolar, no polar molecules. So the next question is, are these things soluble in water? No, they're nonpolar. Are they soluble in alkanes? Yes, because they're fully nonpolar. Melting and boiling point. About the same. About the same as an alkene. So generally speaking, these things will have a melting and boiling point usually within about 5 degrees to at most 10 degrees off from an alkane. So that's our melting and boiling point section. Ready to move on to naming. Okay, so naming. We need to have a root which tells us how many carbons the chain is. So that's that meth, eth, prop, and so on. We then put in a hyphen, and then we put in a number. And a number tells us the location of where the double or triple bond is. Now, if it's a alkene, it will end in E-N-E. If it is an alkyne, it will be root, hyphen, number, hyphen, Y-N-E. And there can be prefixes in those. There can be a prefix tucked in there. And the prefix works the same as it did for the alkyl halides. You can have a dichloro, a dibromo, or you can have a diene or a triene. So you can have multiple double or triple bonds within a structure. All right, moving on. So this is a point in time where you can put away this large piece of paper or set it aside, and we're going to move on to our lined piece of paper. So move on to your lined piece of paper, and on the lined piece of paper we're going to have a bit of a note. So on that lined piece of paper we are going to have a note regarding, did I get the order wrong? Hey, well, I got an extra slide. So, isomers. Isomers, the same number of atoms but a different arrangement of atoms. I'm going to share this slide with you, or PowerPoint with you, so you don't have to copy all this down right this second. The same number of atoms but different arrangement of atoms. Stereoisomers, this is new. Stereoisomers have the same layout but arranged differently in three-dimensional space. So, there are two versions. There is cis, which means same, which means when there is a double bond, cis means the bond is on the same side, or where the rest of the chain goes is on the same side, like this. Like it could be a CH3 group, could be another CH3 group. That would be a hydrogen. That would be a hydrogen. So this would be cis but 2-ene. In contrast, we have trans. Trans means that they are on opposite sides. So you still start with the same double bond. And if we're putting a CH3 group going down, now we're going to have a CH3 coming up. So it's the opposite side of the double bond. And we'll put a hydrogen there and a hydrogen there to complete the thing. So this is now trans but 2-ene. So that's the difference between the stereoisomers. You have the same basic structure, but you can arrange the groupings in three-dimensional space at different positions. And they'll have slightly different reactivities, slightly different melting boiling points, but generally they're pretty similar except for their actual structure. All right, so next, we're moving on to name this, draw that. So we're going to give a few examples of names and symbols, and you've got to draw them. So if we're going to name this, okay, so I'm going to draw a CH3, CH2, CH, nope. Let me redo that. Ooh, didn't mean that fine. CH3, CH2, C, an H down there, double bond, C, CH2, 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 CH3. And the one I'm going to have you draw is F-ine, which is also known as acetylene. Oh, and I missed an H on this left-hand one. Sorry about that. Okay, so when we look at the one on the left and we're going to name it, we can see that the double bond is closer to the left-hand side, so we realize that's carbon 1, that's carbon 2, that's carbon 3. We can see clearly that it's shifted, so we know that they're both on the same side, so that makes this a cis. We count the carbons and we find that there are a total of 8. So this is an oct-3-ene. And for those of you wanting to do a line structure of this, so we would have our 8 carbons, and we'd have to have a double bond. Ooh, didn't do that right. Oh man. I digress. Quickly bring this back up so we now know it is a cis oct 3-ene. And the other one, in order to show that it's a cis, that's 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. Okay, I got the 8. Okay. Ethyne, which is acetylene, we just have to draw it as a line structure. It's pretty simple. All done. As a structural diagram, it's CH, triple bond, CH. Okay, that's pretty straightforward. So let's do another name this. I'm going to give you this time a line structure for you to name. Do it as some black, so it's got a double bond there. As soon as you get into multiple double bonds, we don't have to worry about the cis and trans. And as for the drawing, hex 1, 3, 5, tri. Yep. Not going to make that mistake again. Tri, I, N, E. T-R-I, Y, and E. Not going to risk erasing the whole thing again. Okay, so naming this thing, I got a 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a known. There are 2 double bonds, and counting from the left-hand side, it's on carbon 1. And 1, 2, 3, 4, 5. Diene. And that's it. Hex 135 tri-ine. Okay, so it's triple bond. So if I'm doing a line structure, there's a triple bond, and the single. And there's the triple bond on 3 to 4. There's a single bond between 4 and 5. And a triple bond between 5 and 6. And since it's a hex, that's the whole thing. As for a structural diagram, it's CH, triple bond, carbon, single bond, carbon, triple bond, carbon, single bond, carbon, triple bond, carbon with a hydrogen. All right, so there's some examples of some drawings for us and some names. Moving on in 3, 2, 1, go. Reactions of alkenes and alkynes. Now I said they fall under the normal classifications, and so we'll write our heading of reactions of alkenes and alkynes. Reactions of alkenes and alkynes. What you're going to find is that these are in fact synthesis. Okay, they're synthesis. But for organic chemists, they call them addition. So the general group in organic chemistry is addition. So that's the term that we're going to have to use here. And then depending on what we're adding, it gets more specific. So, example 1. I'm going to, for all of these, use the organic molecule propene. So I'm going to have a CH3, CH, double bond, CH2. So that's propene. I don't have to put a 1 on it because no matter which end of this molecule I put the double bond, it's still going to be a 1. So if the chain is short enough, we don't need the numbers. So propene plus, I'm going to react it with Cl2. The reaction with Cl2 will take place at room temperature. Those are the conditions. And for the organic reactions, we're going to be getting in the habit of writing our reaction conditions. So when this happens, our double bond, the second bond, that pi bond in the structure, is going to break. So I'm going to draw the CH3. I'm going to draw a CH, but where I had the double bond before, I'm only going to write the single bond, not the double. And then the CH2. But off to the side here, I'm going to draw a line down in both cases. That's an indication that I have to add another molecule. So the fourth bond, because carbon has 1, 2, 3, the fourth one is the Cl. The other chlorine atom goes on the other carbon. And so now what we have in name is 1, 2 hyphen dichloro propane. The double bond is gone. The second bond or pi bond has been broken, and we have chlorines attached where the pi bond used to be. So my second example for this, Eg2. Again, I'm going to take propene, CH3, CH2, just CH, now CH2, plus this time around, I'm going to change it to hydrogen. Now, whenever we're going to add hydrogen for any of these reactions, hydrogen molecules don't like being shoved into these things. So it's going to require two things to make this happen. It's going to require heat, which is represented by the triangle, and P for pressure. So our reaction conditions will be heat and pressure. And same as before, we got a CH3, the same molecule we started with, single bond CH. And in place of where that double bond was, I'm just drawing a single with a CH2. And then to show where those hydrogens are, I'm going to put the line coming down off of each of the carbons where the double bond used to be, and a hydrogen there, and a hydrogen there. Now, you would be absolutely correct in saying, well, isn't that just CH3, CH2, CH3, in which case it's propane. Answer, absolutely, it is. I just like to write those extra hydrogens that are being added off to the side so it's very clear and easy to see what it is that we're adding. Okay, now, organic chemists love to name these things. So, because we are adding a halogen, this is called halogenation. And for the second one, because we're adding hydrogen, it's often pronounced hydrogenation. So just like hydrogenation for hydrogenated margarines, it's the same thing. Okay, so that's the first two examples. And now we're moving on to something called Markovnikovs Rule. Markovnikov was you need to copy down the heading. Markovnikovs Rule was written by a Russian scientist by the name of Markovnikov, and the general way, or the colloquial way of writing it, is the rich get richer. The rich get richer. Well, he was living in Tsarist Russia, so the Tsars kept getting richer, so it made perfect sense. The proper way of writing it is when adding comma the hydrogen will go where there is already more hydrogen. When adding, so the addition reaction, the hydrogen will go where there is already more hydrogen. Okay, so my example for this, I'm going to take that propene again. So CH3, CH, double bond, CH2. We're going to add, this time around, I'm going to add an HCl. For those of you wanting to keep track of the name off to the right-hand side, this one is called a hydrohalogenation. And no, I am not making that up. On the plus side, like a halogenation, this takes place at room temperature. Room temperature. And so, like before, we draw our basic structure, which is the CH3, single bond, CH, single bond, CH2, and we draw our lines coming off to the side. And now we look at the HCl and we say, oh, we got a hydrogen and something else. So I now have to figure out where the hydrogen is going. The hydrogen cannot go on the CH3 on the left-hand side. That's not where the double bond was. The central carbon has one hydrogen and the carbon on the right has two hydrogen. That means that the hydrogen from the HCl has to go there. Which means the chlorine has to go on the central one. So that's following Markovnikovs rule. The carbon on the end got richer in hydrogen. Now, these reactions can also work with adding other molecules. Also works when adding H2O or NH3. Okay, so when you're adding H2O, what you have to do is you have to break it up into an HOH, and when you're adding ammonia, you have to break it up into an H and then an NH2. Okay, so that's how that works. Moving on to the next slide. Preparation of alkenes and alkynes. Now, as before, no new reaction types, just new names. This is decomposition. But organic chemists call it elimination. So it's decomposition under the old system. For organic chemistry, we will be referring to it as elimination. And elimination always produces some small inorganic molecule, like a HCl or a water or something like that. So, example 1. I'm going to take, well, one of the ways we can make this is we can take a chemical like CH3, CH2, CH2Cl, and because it's a decomposition, there is only one reactant. And whenever this is going to happen, the reaction conditions will always be heat, that's that little triangle, and concentrated conc H2SO4. Now, in order to remove something, first of all, you look for the functional group, which in this case is going to be the chlorine. And so the chlorine's got to come out. Now, when the chlorine comes out, it's going to bring a hydrogen with it. So the chlorine comes from there to there. We cannot take a hydrogen off of the same carbon, because then that carbon would be short. 2 bonds, not 1. So we've got to take a hydrogen out of here. Which means once we take out an HCl, a small inorganic molecule, we are left with CH3. C. Of the 2 hydrogens in the middle, we only needed 1, so we left 1 behind. And then on the right, we took the chlorine and we left the CH2. Now, when we count, we find that the carbon on the left had 4 bonds, the 1 bond to the other carbon and the 3 hydrogens, but the central carbon only has 3 bonds, the 2 that we see plus the hydrogen, and the carbon on the right has 3 bonds, 2 to the hydrogen and the 1 we see. Which means that in order to complete this bond, we must have a second bond put in right there. So elimination will create a pi bond. Creates a pi bond. And the name of this structure is, of course, propene. All right, so that's all, folks.